Okay, this is Atomic Nuclear Problem Review worksheet, and this is going to be the walkthrough for numbers 6 through 10, excluding number 8, which there'll be an attached video for you guys to look at on that. Okay, so here we go. From an original mass of 64 grams, 2 grams of element X remain after 12 years. Determine the half-life of this element. Okay, so this is a little different process, but again, you know everything's getting cut in half. So in this case, we start with 64 grams, and you know the 64 grams has to get cut in half over and over again. So it gets cut in half in once, and it would be 32. We get cut in half again to 16. We get cut in half to 8. It would get cut in half to 4. It would get cut in half to 2. And that puts us at the 2 grams it's supposed to end up at. So this is 1, 2, 3, 4. 5 times it gets cut in half, which means 1, 2, 3, 4, 5 half-lives have occurred. So now we need to figure out if those 5 half-lives occur in 12 years, what is the actual half-life? So we know that it always starts at time 0, and then 1 half-life, 2 half-lives, 3 half-lives, 4, 5 half-lives, and at the end of those half-lives, 12 years have gone by. So the question is, what time frame is going by over and over again to get us here to 12 years? So if you just take the 12 years and divide it by 5, right, you're going to see that that gives you, I believe, 2.4. 2.4 years. And then we can test that. So if 2.4 years go by, and then another 2.4 years would make it 4.8, and another 2.4 years would make it 7.2, and another 2.4 would make it 9.6. Another 2.4 would make it 12. So that is a correct answer. But you can see what you actually did to solve that was take 12 divided by 5 to find the increments. And we figured out there were 5 half-lives by simply cutting the mass in half until we got to the mass amount. So kind of like the same thing we did with the time to figure out the half-lives, but we've done it with mass here. Okay, moving on. So this is more of a concept question. The gaseous element oxygen consists of 3 isotopes: oxygen 15, 16, and 17. And remember, you're going to need to be comfortable with the number of protons, neutrons, and its tied isotopes. So the first thing is you need to realize what you have here in this format is the mass number. So oxygen 15 has a mass number of 15, and it's oxygen, so it has 8 protons, or an atomic number of 8. And so oxygen 16 also has 8 because it's oxygen, and oxygen 17 has 8. And so when you're looking for the number of protons and neutrons, they're all going to have 8 protons because they're all oxygen. And then hopefully at this point you're comfortable with the idea that to get the number of neutrons, right, since this is the number of protons plus neutrons, you just subtract the protons out. So 8 from 15 gives us 7 neutrons, 8 from 16 gives us 8 neutrons, and 8 from 17 gives us 9 neutrons. And so hopefully you can also see here that the only thing that varies with these 3 isotopes of oxygen is the number of neutrons, which in turn changes their mass number, but not their atomic number. Okay, moving on to 9. So here you have a fossil bone that contains 1/28. So that's a descriptor of the math. It's just a fraction instead of a number. We want to know how old is the fossil. The half-life of carbon is 5,700 years. So what we need to do is just like when we were given the final amount of mass in the other one, we need to take this back to 1, to the whole. So what we do is we run in reverse here. So I'm going to start down at the bottom just so it looks similar to our other ones when we get done. So 1/128. And then if you double that, you get 1/164. And if you double it again, you get 1 1/32. And if you double it again, you get 1/16. And if you double it again, you get 1/8. If you double it again, you get 1/4. And if you double it again, you get 1/2. And if you double it again, you get 1. So that is our original amount of carbon. We start with a whole, right? The amount of carbon in a living organism. And then every 5,700 years, it gets cut in half. So 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5 half-lives, 6 half-lives, 7 half-lives. 2, 3, 4, 5, 6, 7. So all you're seeing here in fractions is just it getting the mass getting cut in half and half and half and half and half again. And now for the time, you can see we just go through those 7 half-lives with our 5,700 years. So 1, 2, 3, 4, 5, 6, 7. Oops, 7, 6, 5, 4, 3, 2, 1. Okay, we always start with 0 time has passed, and that's when we would have 1 or all of our carbon-14. And then 5,700 years goes by, and then another 5,700 years puts us at 11,400, and another 5,700 puts us at 1,700 or 17,100. Another 5,700 puts us at 22,800. Another 5,700 puts us at 28,500 years have gone by. Another 5,700, or 1 half-life's worth of time, is 34,200. And finally, one more 5,700 years goes by, and it puts us at 39,900 years going by. So our answer is 39,900 years old is that fossil. Okay, so I know that one's a little confusing. Probably won't be one with fractions on the test. However, if you're confused, just ask me in class and I'll go over this a little bit more with you to make sure you're comfortable with it. Okay, and finally, this is just your nuclear equations again. I just have a lot of people that don't understand exactly what the question's looking for. So all we're doing is we're writing the nuclear decay equations for what uranium-238 actually goes through. But we're only doing the first 4 steps. I think there's like 28 steps or something like that. You can Google it, or if you want, come ask me and I'll Google it for you and show you. But we're just going to do the first 4, so let me show you what this looks like. So 238, 92 is uranium, and we say the first decay it goes through is an alpha. So you should know at this point, and certainly for the test, that an alpha particle is 4/2 helium. And so remember, these need to equal out, so 4 plus what would equal 238? That would be 230. Oops. Let me erase that. That would be 234. And then on the bottom, 2 plus what would equal 92? That would be 90. And then remember, we find the element that this is by the bottom number, the atomic number, and 90 is thorium. So this is our first nuclear decay. We end up with thorium. Now, thorium then is still unstable, and so it's going to be our next nuclear decay. So thorium-234, 90. And we can see that the second decay is going to be a beta decay. Again, you should know what beta particle is. It's an electron, and the way you write it is 0/-1. And then again, we just do the math. So 0 plus 234 equals 234, and -1 plus 91 equals 90. And so we look this up. 91 is going to be let's see if I can pronounce this correctly. 91 is protactinium, Pa. So that is our second evolution. And then it is still unstable, so it's going to go through a nuclear decay. So 23491. And our third nuclear decay is another beta. So write our beta particle in there. Do the math. 0 plus 234, so 234. And -1 plus what equals 91 would be 92. And so now we've actually turned back into uranium for our third decay. And then the fourth decay is going to be an alpha decay again. So we're going to take our uranium-234 and send it through an alpha decay. So, oops, what's over here? That's our fourth one. And again, alpha particle is 4/2 helium. So when you do your math, 230 plus 4 gives you 234. And 2 plus 90 gives you 92. And 90, an atomic number of 90 is again thorium. And so the end is, you should end up with thorium-230. But again, this isn't the end of the uranium-238 decay. It just keeps going and going through like 28 steps or something like that before it becomes stable. So again, if you want to look at that, just Google it. This is the end of the video. So again, if you have any questions on any of these videos, just ask in class. These aren't the end all. All right, thanks.